Let's take a look at applying the conservation of mass to a particular problem. So in this example, water flows through the pipe such that it has a parabolic velocity profile given by the following equation. R is the radius of the pipe, the circular pipe. V is the velocity in meters per second. Here we want to determine the time needed to fill the tank to a depth of 1.5 meters if we start when the tank is empty, h is 0, at time 0. We're also told that the width of the tank is 3 meters. So it's a 2 meter by 3 meter tank with a height h at any given time, where h is going to be changing, obviously, as the tank fills. So the first thing we have to do in these types of problems is we have to define our control volume. So in this case, I'm going to define the area in purple as my control volume. So this control volume is going to be changing with time, because as the tank fills, the control volume will keep expanding. So if we take a look at our conservation of continuity equation, conservation of mass, this first term deals with the local change of mass within the control volume. So in this case, since our control volume is constantly changing, we're adding mass to it. This term is not going to be 0. We have to take this into account. The second term is the convection of mass through the control surfaces. So if our control volume is defined as here, this is shown in purple, we have water coming into the control volume. So this term will also not be 0. We have to take this into account. Now, one thing we can do right away is, because we're dealing with water and the density is not changing, we can cancel out density on both sides of the equation, just divide through by it. So that leaves us with the integral of dv, which is just a v. So we'll have the partial of v with respect to t. And this side is going to be, we've got two terms, q dot out minus q dot in. Now in this case, we only have water coming into the control volume. We have no water exiting via another pipe or anything, so this term is 0. So finally, we have this equation here we have to solve. So this is the change in volume with respect to time minus q dot n equals 0. Now let's take these one at a time. So here, let's start with the q dot n term. Integral over the area v dA. We can plug in our velocity profile. dA is going to be 2 pi r dr. That's simply it's a circular pipe, so that's our differential area. The integration goes from 0 to 0.1 meters. So the pipe has a 200 millimeter diameter. So it goes from the center of the pipe, which is r equals 0, out to the outer pipe, which is 100 millimeters, or 0.1 meters. So we can perform this integration. We can multiply 3 times 2 times pi, factor that out, integrate, and we come up with 0.015 times pi, or 0.047 cubic meters per second. Now, this term involves the change in volume with respect to time. So at any given time, let's say the tank is filled up to a height of h, the volume is simply 2 meter by 3 meters by h, because we're told in the initial statement that the tank has a 3 meter depth. So it's 2 times 3 times h, or 6 times h. Now the partial of v with respect to t, this is going to be 6 times the partial of h with respect to t. And we can get rid of the partials here, because this is this dh over dt. The derivative of the h with respect to time. So here's our final equation. We put everything together. We can take this term to the other side of the equation, multiply it through both sides by dt. So we got dh. We integrate from 0 to 1.5 because that's our final height that we want. We want to know what the time is when it fills to an h of 1.5 meters. 0 to t. Do the integration and basically solve for t. We get t is 191 seconds, 191 seconds, or 3.18 minutes. Okay, so hope you learned something from this problem. This take these problems step by step and break them down like I did and work each term separately. And I think you'll have good luck with these types of problems.